Alright, so today we're going to do a few slightly harder examples of proving limits using the formal epsilon-delta definition. I wrote out the definition here as a reminder. The limit as x approaches a of f of x equals L. Formally what that means is that for all epsilon greater than 0, we can find a delta greater than 0 such that if this inequality is satisfied, if x is within the delta window around a, then the function will be within the epsilon window around L. Okay? So as a first example, let's prove that the limit as x approaches 3 of x squared equals 9. So we're going to do a quadratic function this time. It's going to be a bit harder than the linear functions that we did last time. But let's just start going through the proof and we'll see what happens. Okay? So proof. How should any proof begin? With the same 3 lines. As you remember from the previous video, first line, let epsilon greater than 0 be given. Okay, that satisfies this part of the definition for all epsilon greater than 0. Now we're finding a specific delta. We're going to let delta equal something. Like before, this is going to be filled in due time. Okay, that satisfies this part of the definition. We're showing that there exists a delta. Now we're going to suppose that this is the case. So let x satisfying that inequality, 0 less than x minus a, in this case is 3 less than delta, be given. And we're going to show that this implies this. So we're going to start off with the f of x minus L now, and we're going to do some algebra and hopefully conclude that we get less than epsilon at the end. Okay? So let's start with our f of x minus L. Okay? These are the same 3 lines that you see in every limit proof. Then you begin with your f of x minus L. And now we're going to go through the algebra. So let's begin. The function is x squared. The limit is 9, or so we claim. X squared minus 9. Okay? Now, what do you think we should do at this point? We have a difference of squares. So a natural thing to do would be to factor that. X squared minus 9 factors into x minus 3 and x plus 3. And the absolute value will split over the product. So we have abs x minus 3, abs x plus 3. Okay? Now, we know something about one of these quantities. We know something about the x minus 3. We know that that's less than delta. Okay? That's part of our given information. We're supposing this before we begin the proof. And in the proof, if we do things correctly, some algebraic manipulations should lead to this term popping out. Okay? That's a good thing. We know that this is less than delta. Now, we want to know something about the size of this. Because unlike in the previous examples we did with linear functions, this is not a constant. If you remember back to the first video, when we were proving limits of lines, we had a constant coming out here, and then we could replace this piece with delta, and then choose our delta to be epsilon over that constant, so then they cancel out. Now, unfortunately, this is not a constant. We can't say that this is less than delta times this variable quantity, and then set delta to be epsilon over the variable quantity. Because delta has to be a fixed number. And this changes as x changes. X is within this little window, and it's arbitrary. Okay? So we need to say something about the size of this. In particular, we want to get an upper bound on the size of that quantity that'll be just a constant. Okay? We want to lose the variable x. So, what do we know about this? Well, we know, for starters, that x is pretty close to 3, right? It's at most delta away from 3. So what can we say about x plus 3? Well, if x is very close to 3, then x plus 3 should be pretty close to 6, right? At most delta away from it. Okay? So what upper bound should we use here? Well, delta is a small quantity. Usually, it's less than 1. I mean, for reasonable sizes of epsilon, if you're choosing a very small epsilon, then your delta should be pretty small as well. Usually that'll be less than 1. Sometimes a larger delta might work, but we're free to choose whatever delta we want. And if a particular size delta works, a smaller one will also work, okay? So we may as well stipulate at this point the delta that we're going to pick is at most 1. That'll give us an upper bound on the size of this term, okay? So at this point, stipulate delta is less than or equal to 1, okay? So what does that tell us? Well, if x is at most 1 away from 3, then x plus 3 is going to be at most 1 away from 6. So the biggest that this quantity can be would be 7. Let's arrive at that algebraically. If delta is less than or equal to 1, what that means is, so let's just do this on the side here, what that means is that x minus 3 in absolute values is less than or equal to 1. Okay? We're replacing delta with 1. Or rather, less than 1 actually. Okay? And now we want to say something about x plus 3. So watch what we're going to do. We're going to do something tricky. Okay? X plus 3, we're going to subtract and add 6 inside the absolute value. We can write x plus 3 as x minus 3 plus 6. Okay? And then this is less than or equal to x minus 3 plus 6 by the triangle inequality, which I'll write down in a moment. And then that is less than 1 plus 6 by that inequality, which is equal to 7. Okay? So x plus 3 is less than 7. And now we can combine these two pieces of information in here and continue with the proof. Okay? So what's all this that I used here? This triangle inequality? Well, maybe I should put it up here. Triangle inequality. It states that for all real numbers a and b, for all a, b, and the real numbers, we have the following inequality. A plus b in absolute values is less than or equal to the absolute value of a plus the absolute value of b. We also have a reverse triangle inequality, which states that the difference between a and b in absolute values is, in this case, greater than or equal to the difference between just the two quantities in absolute values separately. Now, to avoid having a negative here, we could switch a and b. We have a bigger absolute value surrounding this. Okay? So these triangle inequalities come up a lot in limit proofs. Okay? Usually you're going to be using some sort of either one or the other, depending on the proof that you're doing. Okay? Because we do a lot of work with absolute values, and the point in these limit proofs a lot of the time is to find sort of clever upper bounds on things that are variable quantities. Okay? So let's get back to the proof. We have that x plus 3 is less than 7. Okay? And we have that x minus 3 is less than delta. Okay? So at this point, we can replace that with delta and that with 7. Okay? So let's continue here on the next line. This previous part is less than delta times 7. Okay? So 7 delta. Now, we want to conclude that that's less than epsilon. Okay? Remember, at the point where you've replaced all the variable quantities, all the x's have gone away, and you've replaced them either with constants or with some expression involving delta, at that point we're ready to set the quantity here equal to epsilon and then solve for the delta that makes it work. So if we set this equal to epsilon and solve in our heads what does delta have to be, we get epsilon over 7. Okay? So we can plug that in, and we'll get that this is equal to epsilon over 7 times 7, which is equal to epsilon. Okay? And the proof is done. And now we have to figure out what our delta is. Well, on the one hand, we set it equal to epsilon over 7. Okay? On the other hand, we said it's less than or equal to 1. We needed this part to conclude this. Okay? We needed that stipulation that x minus 3 is less than 1 in order to conclude that x plus 3 is less than 7. And that was essential to making the proof work. Okay? So delta has to be smaller than both 1 and epsilon over 7. So it has to be, say, the minimum of those two. Okay? So we're going to set delta equal to the minimum of the set containing 1 and epsilon over 7. Okay? Whichever one of these quantities is smaller will win. If our epsilon is very big, then 1 will be the minimum quantity. And 1 will be used as our delta throughout the proof, and the proof will work. Okay? If epsilon over 7 turns out to be smaller, then we can use that throughout the proof. This inequality will still be true, though. Okay? Because delta is smaller than 1. And there's no point of sort of solving exactly for the best delta which works here. 7 is an upper bound. Okay? As long as delta is less than or equal to 1, which it is if the epsilon over 7 is less than 1. So it's important to notice that there's a lot of freedom with these epsilon-delta proofs. This choice was made by us. We just chose delta to be less than or equal to 1. We could have stipulated that delta is less than or equal to something else, like 2, let's say. So what would happen if we changed that 1 to a 2? Well, from here we would have x minus 3 less than 2. And then following this algebra, we'd have a 2 over here, and then that 7 would switch to an 8. So let's just make that change. Let's see what happens in the proof when we make that change. So we have 2 plus 6 equals 8 now. So this quantity is now bounded above by 8 with our new delta value. Okay? And what do we end up getting? Delta times 8. And now we're going to have to choose delta to be epsilon over 8 instead of epsilon over 7. So that changes, we get epsilon over 8 times 8. Okay? So in order to modify this, if we wanted to change the delta to be less than or equal to 2, we'd now be taking the minimum of 2 and epsilon over 8 instead. Okay? And that proof works as well. So there's a lot of freedom with these epsilon delta proofs. Okay, so before moving on, let's visualize what we've just done in this proof. Okay? So here's a quadratic function x squared, okay? And we just proved that the limit as x approaches 3 of x squared equals 9. So this is what's happening here on the graph. As we're approaching 3, okay, as x is approaching 3, x squared is approaching 9. You can see that. You feed 3 into the function, you get out 9. Now, we've chosen an arbitrarily sized epsilon window around 9. And in the proof, we figured out that the delta window we needed to choose around 3 had this size. It had the size, the minimum of 1 and epsilon over 7. And we can see that in order for every x value from this delta window to be within the epsilon window here, we need the delta window around 3 to be considerably smaller than the epsilon window around 9, especially if we were considering a point further out than 3. Okay? But for 3, this particular delta value works. And we can see that right from the graph that the delta window is about 7 times smaller than the epsilon window around 9. Okay? Now this delta that we found here is not the optimal value of delta that works. In fact, if you look closely at this little window, okay, the optimal value of delta would be the distance here between 3 and this quantity here, such that when you feed it in, you get out 9 plus epsilon, okay? That would have to be our 3 plus delta, okay? This value over here to the left of 3, such that when you feed it in, you get 9 minus epsilon, is further out to the left from 3 than this value here is, than the 3 plus delta is, okay? So in order to find the optimal value of delta, okay, so to find optimal delta, what would we need? We would need a value of delta such that when we sub in 3 plus delta into our function, x squared, out pops the value 9 plus epsilon, okay? Specifically on this side, again, why? Because x squared is increasing faster as you move to the right, okay? So we can solve for this optimal value of delta. Expand this out, we get 9 plus 6 delta plus delta squared equals 9 plus epsilon. and the two 9s would cancel out, and now we'd have a quadratic equation to solve for delta, okay? We could reach the same conclusion if we manipulated our inequalities a bit differently in our proof. So from the proof, if you recall, we had x minus 3 times x plus 3, okay? And we said that this quantity was bounded above by delta. And since x minus 3 is bounded above by delta, x plus 3, from what we did with the triangle inequality, this is x minus 3 plus 6, which is less than or equal to x minus 3 plus 6, absolute value splits, which is less than delta plus 6. Okay? If we simply replaced the x minus 3 in our proof here with delta, rather than stipulating 1 for delta here and getting a constant, we would have delta times 6 plus delta here as our upper bound. And now we could set that equal to epsilon and solve for delta, exactly what we have here, okay? The problem with that approach is it will give you the optimal delta that works, but you'll also have to solve a quadratic equation. So you'll have to do a bit of work on the side, and the delta value that you obtain won't be as nice. It will be, well, the result of solving a quadratic. It might have a square root or something in there, okay? And also, there's no real point to that. When we're looking for a delta, we need to find a delta that works. It doesn't have to be the optimal delta, okay? In this case, for the linear function, it might be easy to find the optimal delta. In the quadratic case, it's not so easy. And for other functions, it might not be possible at all, okay? So the solution that we had here, where we set delta to be the minimum of 1 and epsilon over 7, that'll give us a window that is strictly inside this little window over here. It might be much smaller than the optimal delta. For instance, if you think of epsilon as being very large, then quite a large delta window around 3 would work. That would be the optimal delta window. But we would choose 1 in that case, okay? When would we choose 1? Well, if epsilon is greater than 7, okay, then we choose 1. So if the epsilon is considerably large, we'll expand the delta out a little bit, but we won't go past 1. So our delta might be far from optimal, but again, that doesn't matter because we're not looking for the optimal delta, we're looking for any old delta that works. Okay, so let's prove more generally that the function x squared is continuous at all the real numbers. Okay? So we're going to prove that f of x equals x squared is continuous on R. What does that mean to be continuous? We need a little definition. So firstly, f is continuous on R if f is continuous at every point A in R. And what does it mean for a function to be continuous at a point A? Well, f is continuous. The abbreviation for that is cont. F is cont at a point A if the limit as x approaches A of f of x, the limit as x approaches A of the function is equal to the value of the function at the point A, is equal to f of A, okay? And this is a limit, so the formal definition of limit comes in here, okay? So this again is true if and only if for all epsilon greater than 0, there exists a delta greater than 0 such that, our usual definition, x minus a less than delta implies f of x minus f of a is less than epsilon. So we're just taking our old definition of limit and substituting f of a for L, and we're also dropping that little requirement that x cannot be equal to a. Because in this case, it can be equal to a. This will just then be 0. Okay? There are many ways that this could fail, by the way. The limit as x approaches a of a function could exist, and the value of the function at the point could not exist. Like say you have a function with a hole or something like that. The limit would exist, but the value wouldn't exist. And sometimes we also have a case where the limit exists, the value exists, but they're not equal. Say if you take your hole and fill it in somewhere else rather than in the proper space that you should. Okay? So that's continuity for you. Okay? So in this example, we're going to prove that the limit as x approaches a of x squared equals a squared. And we're going to do this for all a in the real numbers. Okay? So let's go through the proof. The usual 3 lines. Let epsilon greater than 0 be given. I'm going to continue on this line so we don't have to scrunch things in at the bottom. Let delta equal something, which we'll figure out, and let x satisfying x minus a less than delta be given. And now let's proceed with the proof. So we're going to start off with the function minus the limit, okay, x squared minus a squared, as usual. And now we're going to proceed in a similar manner to what we did with the first example. So what did we do with our x squared minus 9 in the previous example? Well, we factored it, for starters. This factors as well into x minus a, x plus a. Okay. Now, this term we know something about. We know it's less than delta. And this term is the one that we need to find an upper bound for. So, as in the previous example, we can say something about the size of delta. We can stipulate that delta is less than or equal to 1. That's the usual value that's chosen. Okay? Although, we could also stipulate that delta is less than or equal to 2, or 3, or anything else. So, let's stipulate at this point that delta is less than or equal to 1. Okay? Then what will follow? Well, x plus a, which by the way is equal to x minus a plus 2a, will be less than or equal to x minus a plus 2a by the triangle inequality. And that's going to be less than 1 plus 2 times the absolute value of a. I just pulled the 2 out of the absolute value and replaced 1 for delta here. Okay? Using this, replace 1, put that in there. Okay? So x plus a is less than 1 plus 2a. And now, continuing with this line, this is going to be less than delta times 1 plus 2a. Okay? Each piece is less than the corresponding piece here. That's less than delta. That's less than 1 plus 2a in absolute values. And now we've lost all our x's. Okay? And we're ready to choose the value of delta that we need. And what delta do we need here? Epsilon over 1 plus 2a. Okay? So that's going to be equal to, or rather less than or equal to, since delta will be a minimum. Okay? Epsilon over 1 plus 2a times 1 plus 2a, which equals epsilon, and the proof is finished. Okay? So which delta do we need? The minimum of 1 and 1 plus an epsilon over 1 plus 2a. There we go. The proof is done. Now you might be wondering about this. Why do we have an a in our expression for delta? Well, there's nothing wrong with that. Okay? If a was a number, like if a was 3, let's say, then look what would happen. If a was 3, then this denominator here would be 7. And we would have the same proof as we had previously. Okay? We proved before that x approaches 3 of x squared equals 9, and we had that value, epsilon over 7 in our proof. Okay? So in general, because the quadratic function increases rapidly, more rapidly for larger values of a, we need our delta window to not only depend on epsilon, but also on the size of a. So there's nothing against the rules about having the actual value here, the a, in our expression for delta. Okay? We just can't have an x in it. X is a variable, whereas a is fixed. Okay? And because this proof works for any a in the real numbers, we've shown that the limit as x goes to a of x squared equals a squared for any real number a. and that proves that the quadratic function x squared is continuous. All right, so as a last example, let's prove that the cubic function is continuous. This will be just a little more algebraically difficult than the quadratic function. Okay? I'm going to prove that the limit as x approaches a of x cubed equals a cubed for all a in the real numbers. And let's do this in two different ways. Okay? So starting with the first approach, proof. This will be similar to the method we used to prove the quadratic. Let epsilon greater than 0 be given, and let delta equals something. Okay. Suppose x satisfies x minus a less than delta. What can we say about x cubed minus a cubed? Well, as with the quadratic, we can begin by factoring this quantity. This is a difference of cubes. X cubed minus a cubed factors into x minus a, and x squared plus ax plus a squared. Okay? Good, bad. Okay, we know something about that. We know it's less than delta, but this looks awfully complicated. Good thing is we can simplify it considerably. So let's begin by using the triangle inequality. Okay. So here we have delta. We might as well sub that in right away. Why not? This is less than delta times, and then that part we're going to expand out using the triangle inequality. Okay? So this will become the absolute value of x squared plus the absolute value of ax plus the absolute value of a squared. Okay? Just because there are three terms doesn't mean the triangle inequality doesn't apply. We just apply it separately to these two terms in the last term, and then these two terms separately. So really there was a double application of triangle inequality here. Now, as one last step, we can pull the squared out of the absolute value, and we can also split this absolute value into two. Okay? So this will be simply equal to delta times x in absolute values squared plus the absolute value of a times the absolute value of x plus the absolute value of a squared. And now what we need to do is get an estimate on the size of the absolute value of x, because that's the only thing that comes into play here. Once we get an estimate on x, then we could replace that x squared and that x there, and then we'll have everything in terms of either numbers or the constant a. Okay? And then we'll be almost done with the proof. So how do we get an estimate on the size of x? Well, as before, we need to specify a largest delta. So one worked previously, it works again here. Stipulate delta less than or equal to 1. Let's see what that gives us. Well, x is going to be equal to x minus a plus a, we add and subtract a, which is less than or equal to x minus a plus a in absolute values with the triangle inequality. And that's going to be less than 1 plus a. Okay? And now we can substitute that in here. So this will be less than, if we make that substitution, delta times x squared, so 1 plus abs a all squared, plus a times 1 plus abs a, plus abs a squared. And now we can finish the proof by setting delta equal to epsilon over all of this junk. But that doesn't look too nice because there's a lot of junk here. So one way to simplify this would be to make the observation that a in absolute values is less than 1 plus a. So we can simply replace these two a's we see with 1 plus a in absolute values. Okay, so here we can put in a little star. Notice that a is less than 1 plus a, or abs a is less than 1 plus abs a. Okay? This may seem kind of stupid, but it helps clear this up. Because what do we get? we get less than delta times 1 plus a squared plus, this will get replaced with 1 plus a, so we'll have another 1 plus a squared, and then that'll get replaced with another 1 plus a, so we're going to have 1 plus a squared a third time, so we're going to have actually 3 copies of 1 plus a here, okay? Let's get rid of that bracket, times 3 1 plus abs a squared, okay? And that looks a bit nicer than all of this stuff, okay? But, of course, we could have expanded this out and collected our terms and had a quadratic expression in abs a, okay? So now, we're going to choose delta to be epsilon over that. So this is less than or equal to epsilon over 3 1 plus abs a squared times 3 1 plus abs a squared, which equals epsilon, and the proof is complete. So which delta do we choose? The minimum of 1 and epsilon over 3 times 1 plus a squared. Min 1 epsilon over 3 times 1 plus a squared. Okay. Now the good thing about this approach is that, first of all, this proof works for all a in the real numbers. Okay, so we've proven that the cubic is continuous. And it also generalizes to higher powers of x. So you could use a very similar technique to prove that something like x to the 4th is continuous, or x to the 5th, or a general power function. And in fact, if you want a little challenge, prove that x to the 4th is continuous using the same technique. So just imitate this. The factoring will be a bit different here. There's going to be 4 terms now, but the argument will be essentially the same. Okay? And the same trick, this one, can be used to simplify the expression that you get at the end. Okay? So try that for yourselves. The last thing I want to do today is present a slightly different proof that x cubed is continuous. One that will work for all a except a equals 0. Okay, so last example. All right, we're going to prove that x cubed approaches a cubed for all a in the real numbers except at 0. The proof that we're going to show will work for any real number, but it won't work at 0, and we'll see why. But then we'll come back and do that separately. Okay? So, same lines as usual. We start off with x cubed minus a cubed. Factor as we did before. X minus a, x squared plus ax plus a squared. Now we're going to use the triangle inequality, like we did before. This was less than or equal to x minus a times, what was here? X squared plus ax, both in abs values, plus abs a squared. Okay? And now we're going to stipulate something different. Okay? Instead of saying that delta is less than or equal to 1, less than or equal to some fixed value, we're going to stipulate something variable. Okay? So we're going to stipulate the delta is less than or equal to a. Right? Absolute value of a is a positive quantity for any a that you choose, except for the case that a is 0. So this is why the proof is not going to work for a is 0. But for any other a, this is fine. Okay? Delta can now be larger or smaller depending on the value of a. So we're not stipulating less than some fixed quantity 1, but less than a variable quantity, which depends on a. Okay? Which is fine. And this will cause that part to simplify even further. So the proof will maybe look a little bit nicer even. Okay? So we're going to stipulate that delta is less than or equal to a. And then what do we get from that? Well, we get that x, which is equal to x minus a plus a, which is less than or equal to x minus a abs plus abs a, is in fact going to be less than 2 times the absolute value of a. So this is a common trick, by the way, in these limit proofs. If you want to get an upper bound on some quantity, you might have to add and subtract something to the absolute value and then use the triangle or the reverse triangle inequality and conclude. Okay, so keep this trick in the back of your head, the adding and subtracting of the same thing. Okay? And of course, keep the triangle inequality in your head. Very important. You'll see in future videos, it's used all the time in these proofs. So let's replace our abs x with 2 abs a in here. Well, this is going to be less than, that's less than delta, and this part is going to be less than 2a in abs values all squared plus a times 2a in abs values plus abs a squared. That's 4 abs a squared, that's 2 abs a squared, that's abs a squared. This is equal to delta times 7 abs a squared, which is, by the way, the same thing as a squared. Okay? The absolute value squared is the same thing as the quantity squared. Okay? So we have an expression which is a little bit simpler for delta now. Okay? Because we're now going to substitute delta equals epsilon over 7a squared. And the 7a squareds are going to cancel out. This will be equal to epsilon, and the proof will be finished. Okay? So delta will be, in this case, equal to the minimum of abs a, rather, and epsilon over 7a squared. And that's the end of the proof. Now, if we want to finish this off and make this work for proving x cubed is continuous on R, we have to consider the case of a equals 0 separately. All right, so let's finish off the example. We want to prove that the limit as x approaches 0 of x cubed equals 0. Okay? Our famous 3 lines are in place. Let's proceed with the proof. We want to show that x cubed minus 0, the limit, okay, is less than epsilon. Okay? So x cubed minus 0 is just x cubed, which is the absolute value of x cubed. The cube comes out of the absolute value. And now we know something about the size of the absolute value of x. From here, we know that the absolute value of x is less than delta. The 0 doesn't make any difference. So over here, we have that x is less than delta, so x in abs values cubed is less than delta cubed. And now all we have to do is set delta cubed equal to epsilon. Okay? So what does delta have to be? The cube root of epsilon. So this is going to be equal now to the cube root of epsilon cubed, which is equal to epsilon, and the proof is finished if we set delta to be equal to the cube root of epsilon. Okay? So there doesn't necessarily have to be a linear relationship between delta and epsilon. We can have a square root or a cube root sometimes, depending on the function we're working with. In this case, it's perfectly valid to have an epsilon cubed come up in our proof and have to set the delta equal to the cube root of epsilon. Okay? This mini proof plus the previous board combined together prove that x cubed is continuous for all a.